Hello everyone. In this short video, I'll run through the specifics of wind load calculations as defined in the Eurocode for canopies applied to a Karamba3D example file. For the geometric definition of this example, please watch our previous video. There is also going to be a follow-up looking at the application of the wind load to the example, so please subscribe to catch that when it is released. This video specifically covers wind load definition based on Eurocode 1, Part 1.4, General Actions, Wind Actions, and we're looking at section 7.3, Canopy Roofs. Canopies are defined as the roof of a structure that has no permanent walls, and it is applicable to structures such as carports, gas stations, shading structures, and so on. Finally, we're only talking about a specific type of canopy, dual-pitch canopies. These are essentially V-shaped or inverted V-shaped canopies which feature two distinct angled surfaces. First, we will take a quick look at the Eurocode clauses, and then we will dive into the example file where we use a small C# script to determine wind loads which parametrically depend on the geometry of the canopy. The first parameter that needs to be considered is the degree of blockage. As it is shown here, the degree of blockage is defined from 0 to 1, where 0 means a completely empty freestanding canopy, unobstructed by anything underneath, and 1 means the canopy is fully blocked on the downwind eaves by various items. The engineer also has the option of interpolating between those values in their calculation. An important assumption that we're going to make is that the overall force coefficients that we determine are used to calculate the resulting force on each of the canopy surfaces. The most important geometric parameter that we need to look at is called the roof angle alpha, and the Eurocode gives us details for angles in a range of -20 to +30 degrees, where negative means a V-shaped canopy and positive means an inverted V-shaped canopy. Our goal is to determine the overall force coefficients, and in order to do that, we need to look at table 7.7. In terms of sign convention, positive values indicate a net downward action and negative values indicate a net upward action. So positive values represent the pressure force down onto the structure, whereas negative values represent suction up from the structure. For each angle value, we have a positive force coefficient CF max for all blockage levels. Similarly, we get a negative force coefficient CF min for zero blockage and a CF min for full blockage. And for blockage between 0 and 1, we have to interpolate the values. All of this is relatively simple, however, implementing this in reality could mean that you have to interpolate at a number of levels in between angles, in between blockage factors, and put that all together to get a CF max and a CF min overall force coefficient. One final thing to highlight in terms of the Eurocode clauses is the arrangement of loads obtained from force coefficients. The Eurocode prescribes 6 load situations for a dual-pitch canopy, and they are shown here. We have a pressure on both sides at the same time, pressure on each of the sides individually, suction on both at the same time, and suction on each of them individually. And this is irrespective of whether it's a V-shaped or an inverted V-shaped scheme. It's essentially 6 different load situations that we need to cover. Just to note that we are ignoring any friction forces, we're ignoring any potential openings in the canopy, and any sort of flow disturbance for the wind loads. We're also ignoring multi-bay canopies, which are also covered in the Eurocode. When we jump into our example file, we can see all of this implemented. First, we got some basic parameters that we've talked about. We've got the degree of blockage going from 0 to 1, and we've got a peak velocity wind pressure in kilonewtons per meter squared, which we will be referring to in the next video. The third major input is actually calculated based on our geometric definition, and it's the pitch angle that is negative when V-shaped and positive when inverted V-shaped. What we also did in the example is we hard-coded the values from table 7.7. Each set of data is in a panel in list form, following the list of angles provided by the Eurocode. For each angle, we have CF max, we have CF min for zero blockage, and CF min for full blockage. And the key calculation outcome is to derive the minimum and maximum force coefficients for the given angle and blockage factor. An efficient way to achieve this was to write a little C# script that takes in all the Eurocode data and the example-specific data and that does the calculation for us. What we get is those two values of CF_min and CF_max, and we also get a little info panel with some quick, useful output to review. Now let's see this in action. We are changing the cantilever tip rise, and for a given span that automatically changes the angle. As we scroll through some values of the tip height change, we can see the angle and the net downward and net upward force coefficients change. We are also schematically visualizing the degree of blockage, and changing this between 0 and 1 is seen to modify the net upward force coefficient, CF_min, but not the net downward coefficient, CF_max. This is behaving as expected. Let's briefly run through the C# script. Our inputs are the two example-specific inputs, the angle and the blockage degree, as well as the hard-coded Eurocode lists with values from table 7.7. We then perform a little bit of validation. Firstly, we check that the Eurocode data lists are matching in length so that we have values for all the angles. We then move on to applicability. We check if the calculated angle falls within the -20 to +30 degree range. If it doesn't, the canopy is too steep and the method is not valid. We also check to see if the angle is between -5 and +5 degrees, in which case the canopy is too shallow and other methods should be used. And finally, we want to make sure the degree of blockage provided is between 0 and 1. We then move on to the actual calculation. The first step is to find the bounding interval in the angles list for our input angle. We can then derive an interpolation parameter t, which we use further for our force coefficients. We interpolate directly the value of CF_max using t. We also interpolate twice for CF_min at blockage 0 and at blockage 1. And then for our specific input blockage, we interpolate once more to get our CF_min. We do a little bit of rounding of the results and output data is okay and calculation method is valid together with our final values of CF_max and CF_min. For our final step, let's look at an exact example and trace the values through the calculation. For this specific tip rise, we get a pitch angle of -17.5 degrees, which means we have a V-shaped canopy. It also means our angle sits exactly in between index 0 and 1 in the list of angles provided by the Eurocode. This means that for the force coefficients, we have to interpolate between the values in between index 0 and 1. So for CF_max, we get 0.6, which is the actual final net downward pressure coefficient we get from our C# script. And for CF_min, we do it first at 0 blockage, where we get -0.65, and we do it at full blockage, where we get -1.35. And because our blockage is 0.5, or 50% blockage, we interpolate between those two values to get -1, and that's our final net upward pressure coefficient that comes out of our C# script. The next step will be to use the force coefficient to define mesh loads for the 6 loading conditions prescribed by the Eurocode. Thanks for watching, make sure you subscribe, and see you at the next video where we continue this 3-part series on wind loading for dual pitch canopies according to Eurocode.